Hello and welcome back to Humans versus AI. This is video 16. We've kind of achieved the objective of this first phase of this series by getting an AI to play this bespoke game, playing against itself and playing against a human. But I got there because I knew how to do it and how to set it up. The tools that you need to be able to get to where we got to in this series in 15 videos haven't been explained. One of them is to create a two-dimensional rendering of the reward landscape, which I've shown in previous videos. Another one is to create a plot of the reward over time to make sure that the reward you're giving the player makes sense. So we need to create that as well, because you could be doing things that aren't having enough of an impact compared to other components of the reward. And you might be wondering, why is it not learning from this? And the reason is obvious when you plot the reward landscape, both in time and in space. And finally, what we haven't done yet is we haven't terminated the model training at the right place, which we'll do in a later video. So we've still got a few bits to tie off. In this video then, we're looking at rendering the two-dimensional landscape of the energy, which we'll keep quite brief because it's very specific to this game. Okay, I have a Patreon account, of course. If you'd like to contribute to my work, this is where to do it for the time being, and thank you for those who do. Right, let's get started then and try to get this done quite briefly. The objective of this video is to create this rendering. This rendering is what I call the energy density or the energy signature. Each cell of this contour plot represents the energy that the player sees at that position. If the player were here, they would see that level of energy, which is, I don't know, around 1.5. It's calculated by taking a position in each cell and adding up the energy from every single energy point when it gets to that energy cell. If you remember, the energy decays in space exponentially from a given energy point, so it gets lower and lower and lower and lower, as they all do. So you can pick a grid cell and add them all up. And that's what we're doing. The darker the color, the higher the red, the more red, the higher the energy density. So you can see when you're actually sitting on an energy point, which is close to other energy points, you've got a really deep red because the energy is just very high at that point. This is what the game is basically learning from. It's not what the player can see, but it's what we're trying to get it to learn, which is, this is good reward. You want to go over here. You don't want to go over here. If you recall, the player gets a reward through movement. So it calculates at the moment the delta for where the player is to where the player wants to go. So it would look at the difference between the two, offering a positive reward for moving up the energy density, a negative reward for moving down it or away. So we want to create this rendering. So how do we create it? This is a contour plot produced in matplotlib. It's a good tool for rendering things like this. And it's created by placing the player in every grid cell and using our existing calculate reward method to calculate what the reward is for every grid cell. We want to use the same method because we don't want to create two copies of the same thing because they are likely to diverge when mistakes happen and we forget to update the plotting version. So we want to use the same method that calculates the reward, but we do need to use it a little bit differently. So we'll look at that in a minute, but it's fairly straightforward. So that's what we're going to create. First things first then, we need to install the matplotlib library. So in PPO, which is where this is all going to happen inside the wrapper, we've installed matplotlib. So you'll need to go to your virtual environment and install it. I use pipenv and I would do it as follows. You would want to pin the dependency, the one that works for sure with the existing dependencies is 3.10.0, so you can install it like that. If you're wondering how you find out that number, if you were to just install it without the version, you would find that pipenv would pick an appropriate version for you based on what dependencies are already installed. That will then be located in the pip file.log, which you can then search through. So if I were to search for matplotlib here, I can find it, and if I were to scroll down, I would find the version that's used. Now, of course, it matches what's in pip file because I've pinned it, but if it didn't, you'd have a version in there which you could then copy and paste into your pip file. Your pip file is where pipenv gets its versions from when it creates a new virtual environment and when it installs the dependencies. So this needs to be set, basically. So that's how it's done. Right, so assuming you've installed that then, just a few bits we need to change here to make this possible. The first one is, because we want to use calculate reward, which we need to use the same reward calculation, of course, as mentioned, we're going to add an attribute or an argument to its method, simulation. What simulation is, default by false by default, sorry, What it is it's saying if we're simulating the reward grid, we want the behavior to be slightly different. And we use that logic down here. So if simulation is false, which is default, this is the code that's run. It's standard code you've seen before. Nothing else has changed. This is just the calculation of the delta for the player's current position versus where it intends to go, the next position. So that's the delta piece that gives us the reward, if you recall. And we say, well, okay, that's what happens normally. But if we are simulating the calculate reward method, we're not using it for training, then I actually don't want the delta, which is here. I want positive movement reward to be equal to the current player position. Because as you know, what we're going to do is we're going to move the player's current position across the grid, and we want to calculate the energy at that point. So that's why we're not calculating the delta, we're calculating the absolute. That's the only difference here. Now, of course, this method returns reward, which has 3 components. This one won't do anything because it only happens when we when we collect energy, so that won't happen. Long journey penalty will be subtracted, but we want it to be because it's part of the reward landscape, and positive movement reward will be an absolute value as mentioned, which means reward is the absolute energy at that point for a player. So that's what it will produce for the given player position, current X and current Y, rather than the delta. Okay, so that's the first thing we've changed. Now there are 2 new methods to make this work, which we'll talk about very briefly below. I've got to find them first. Calculate reward landscape. This is the thing that loops over calculate reward. We'll talk about what calls this in a minute. But basically, what we do is we grab, we create an empty reward grid using numpy. We fill it full of zeros at the dimensions of our grid. First thing we do, we call it reward grid. That's what we're going to populate. That's the thing we're going to render. We're going to populate it by moving the player across the grid, of course. We save, this is an interesting point, we save, and very specific to my game, we save the player's existing position and we call it player original X and player original Y. That's player zero's current position, and we restore it down here. That's because we are going to be running this before we train the model, and we don't want to move the player's current position because we want the rendered scene to represent what is actually going to happen in the first iteration. So we just basically restore the current position because of course we're going to move the current position. That's the whole point. And that's what we're doing here. So what this bit is we're looping through every grid cell, as I said I would do, and we're moving the current player's current position in X and Y incrementally. And after it's moved, we're populating reward grid with the output from calculate reward, which we've just talked about, setting simulation to true. So we get the absolute value and not the delta. Okay, excellent. So that hopefully makes perfect sense. That's how we calculate the reward landscape. And then here's the method that runs it, that we're going to call from main in just a minute. So what this does is, first off, you get your reward grid, which is using calculate reward landscape, which is what we've just created, which calls calculate reward. So that's the reward grid, a 2-dimensional grid, numpy array, basically, which we're going to render. We grab the player positions as well, and we grab the energy points, because as you know in my rendering, I have not just the energy grid, but also the player positions and the energy points. So we need to grab them before we plot. And this is basic matplotlib stuff. We create a figure of a given size. We have to rotate the grid, the reward grid, because of the way that matplotlib has a different coordinate system. So this was actually trial and error for me to get it right. So you may find the same thing, but I'm just basically flipping and rotating the reward grid array so that it aligns with what we expect, the way it should look. It's not wrong in a different configuration as such, it just won't line up with these points. So I had to do a bit of flipping and rotating because of that difference. And then we just render it, which is what we're doing here, which is using image show matplotlib method to render the grid, to add a label, to add a title, and then we use the scatter plot features to add players and to add energy. And I won't go through the details of that. It's matplotlib basically, pretty standard stuff. You've got basically rendering arrays on top of this contour plot, and that's it. And then we save it. We save the plot, and as you can see, reward landscape with reference is fixed, which is the name we've given it. It's that Simple. Now, what runs this? Well, this is run in main. So if we go to the entry point of the game, main at the bottom, as you know, we've got a bit of logic which says if we're training, we run the train process, which involves creating a wrapper around the game. If we're playing it, we just basically instantiate, set up and run. So within train then, the new bit is this line here. We visualize the reward landscape, the method I've just shown you, and it happens right before train model, which is why I don't want to change the current player's position permanently. So this brings to an end this video. I hope you've enjoyed it. In the next video, we're going to look at rendering the reward landscape in time, which is very, very important if you want your reinforcement learning model to converge the way you want it to. So great, thank you very much, and I'll see you in the next video.